Hello, pre-calculus student. This video is for chapter 4.7, application of log and exponential functions. We will go over several application of exponential function, and lastly, we'll go through logistic model. We don't have any log function application that I have selected. If you want to, you can read the textbook. So in this video, we talk about compound interest application. In chapter 4.1 or 4.2, you should have learned about the formula of calculating amount of investment after periodic compounding. And this is the formula. A equal to P, 1 plus R over N and T for compounding monthly, compounding quarterly, those things. And also there is another formula for compounding continuously, which is A e to the AP e to the RT. I need to connect my pen into it because I can't see my pen. Yeah, okay, it's better. So this is the formula. A equal to P e to the power RT for continuous compounding. So in chapter 4.1, we have been just using this formula, plug in T to find the amount, or sometimes find the rate, or find the P, but we never find time. That means if I want to have a target amount that I want to save with either formula, how do I find out the time that would allow a initial investment to save to a certain value? That's the first thing we want to do. The other one is what is the doubling time? Because when you tell people, oh, it's paying 4.2%, no, yeah, it is. You can tell that every year you get 4.2% more, but it's not as graphic as knowing how long it takes to double your amount because you can use it to compare and it is more uh, concrete as to how your money grow. So we will look at these applications for both periodic compounding and also continuous compounding. So example one, to solve for t, because your goal is to solve for time. An amount of 7,000 is invested in account paying 4.2% interest compound quarterly. We already know that is using the AP 1 plus R over N formula. In how many years will the amount grow to 9,000? So this is the initial investment. This is our future A, and R is change it to decimal 0.042. Compound quarterly means every year I get 4 times of interest, but how many year, that means time, is the unknown. So I'll set up the equation, which is 9,000 because that's A, right? Equal to 7,000, the initial value, 1 plus using this 42% divided by 4, and then 4t, right? So maybe I'll erase this A get into the way. Just say A here. So this is the equation. The t is in the exponent, so obviously it's an exponential equation. So to solve it, we can make this as the b. This is something, this is known, we just did not calculate it. Just keep it that way. And then divided by, clean up the 7,000 before we add log, because we have learned to solve this kind of equation, we divide 7,000, the clean up. So you can simplify a little bit to make it 7 over 9, because divided by 1,000 would be 1 plus 0.042 over 4 to the power 4t. So this is this is the b to the t, you're going to see kind of question. So we'll do ln. We'll do log. Add log to both sides, log and log. After that, we'll have log 9 over 7 equal to log 1 plus 0.042 over 4 to the power 4t. Okay, continue on this side. So the 40 is inside the log, so we can move it as an exponent. So now we have log 9 over 7 equal to 40 times log this whole bunch of 1 plus something, 2 over 4. Okay, so to solve for t, so this is a number that I just haven't entered into the calculator. So your t would be using this log in the top of the numerator divided by 4, open parenthesis, 4 and log 1 plus 0.042 over 4. So it's just a matter of putting in the calculator. I'm going to show you. So t equal to what? Round to 1 decimal place. It's over here. So enter it. So I would do log, just log, open parenthesis. Oh, they have it already. 9 over 7, close it. Divided by, I have to open because I have to do 4 times. Log again. Now this one is really long. 1 plus 0.042 over 4, like that. And then close it again. 6.0, 6 year. So in 6 year, it would grow to $9,000, $2,000 more. Okay, so what's the doubling time? Because when you tell people 4.2% is not very concrete as how things grow, but if you tell people that is double in that many years, is very concrete. So we would say doubling is 7,000 times 2 is double, equal to 14,000. So we would write 14,000 is equal to 7,000, 1 plus 0.042 over 4, 40. We'll divide 7,000 over. That's 2, because this 2 times 7,000. Equal to 1 plus 0.042 over 4 to the power 40. Okay, log again. Log 2 equal to log 1 plus 0.042 over 4 to the power 40. Move over. Log 2 equal to 40 times, move the 40 over by log property, 1 plus 0.042 over 4. Okay. And then, so we would just divide. Will be log 2 over, remember the parenthesis, 4 times of log 1 plus 0.042 over 4. And that's it. Okay, so put in the calculator. So we would just do log 2, close it, and then divide, open again, 4 times log 1 plus 0.042 over 4. Yes, close one more. 16.6 year. So in 16 year, it would be double. Okay, so you would know, oh, after 6 years, there's not even a 1/3 of it. So it's more graphic as to know the magnitude. If you just say 4%, you have to like pull out your calculator and figure out how much it is after 6 years and stuff. But this would be like give you a more concrete sense as how much you will have. Okay, because doubling, people can tell. Okay, so the example 2, this is the same thing, but the compounding is continuous. So we also want to know the doubling time and also how many years would grow to a certain amount. So the formula that we'll use is A equal to P e to the RT, right? So in our case, this is R equal to 0.045. This is a larger one. this is initial P, this is A. So we set up the equation as 5,000 equal to 3,000 e to the 0.045 times t. You can see it's much easier when you're using e as an exponent. There's no divide by n, no parentheses. So to solve this, we divide by 3,000 on this side. So be 5/3 equal to e to the 0.045 t. So this is base e, so we do ln. ln 5/3 is equal to ln e to the 0.045 t. Move it. ln e is 1, so that means ln 5/3 is equal to 0.045 t times 1. And I don't have to write it. So t would be equal to just divided by the rate. ln 5/3 divided by the rate of 0.045. You see, so much easier. So using e as a base is very good. So remember it's ln, don't you? Okay, L5/3 divided by divided by 0.045. That's it. 11.4 year. That fast? That many? Oh, because it's almost double, right? You do 11.4 years. Okay, what's the doubling time? So we set up the same thing. Doubling means 6,000, right? So 3,000 times 2 equal to 3,000 e to the 0.045 t. It's almost the same as this. Divided by 3,000. Divided by 3,000. That's 2 equal to e 0.045 t. Do ln. ln 2 equal to ln e to the power 0.045 t. The t move out, that means ln 2 equal to 0.045 t times 1. And then we just divide, right? So ln 2 divided by 0.045 would equal to t. As a matter of fact, this is a very good formula that you should know. Okay, ln 2, if you want doubling time of any ray, so you see it's just divide by the ray, right? 0.045, 15.4 years. So in 15 years, the any investment is going to double. T equal to 15 year. So when we solve this, I use 0.045. You can actually put it as R. So the side effect of doing this problem is ln2 over R is equal to doubling time for continuous compounding. For continuous. And you can use it to approximate periodic compounding. So if you say, people say, if you want something to be, okay, ln2 divided by 0.07, it's around 10 years. So if you get a 7%, you double in 10 years. So this is like the what is it called, the street smart thing that, oh, if you want something to double in 10 years, you use 7%. And the reason is ln2 over the rate is the doubling time. So if your bank give you any rate like 5% or 5.6%, you can just pull out your calculator, ln2 over it, that would be the doubling time. And in general, you can use it not only for investment, but for other growth or decay. So let's look at all the application of like population or radioactive compound growth and decay. So the most of the time we have three choices of doing growth or decay. In general application, you can use continuous compounding A0E of KT if you know the continuous growth rate. Doubling time is, if you know your doubling time, of course, if you know your growth rate, which is y equal to a 1 plus r to the t also, this is the O1. So you can still use it. So, but a lot of time, if we know doubling time, the number is A0, 2 to the t over the doubling time. If you know half-life, the y is A0, 1 over 2 t over h. So in the next video, we'll talk about how to work on this application related to population and radioactive. What? Let me see. Oh, here.